Oh, fine. How are you?
I'm also fine, sir. So what's time there, sir?
What time is it? It's 8:30 in the morning, so it's okay now.
Oh, okay.
A couple hours ago, it was very early.
Okay. So I request Professor Chakravarti to introduce our next speakers.
Hi, Larry. This is Kalyan Chakravarti. Really happy that we could get you at ICCGNFRT.
Oh, I'm very happy finally too.
Yeah, but I remember that, all three previous occasions I had written to you, but because of your classes or whatever it is, it could never happen that you were being a part of this conference. But I'm so happy that this time, by this online method, but still you are a part of this conference. So really happy to see you here.
I wish I were there, but this is the best substitute. Yes.
Yeah. Now, anyway, there is no other option. We have to be online only. But let's hope that next year, maybe it'll be a little better.
So will there be a conference next year?
Yeah, sure.
Oh, good.
Sure. It will be there. Or maybe I can stand here. Yes, it's time. Yeah, I'll just take 1 minute, Professor Washington, before I introduce you, and then you can start.
I assume my slides are showing up?
Yeah, it's perfectly fine.
Okay, good.
Yeah, it's time, and so it's my pleasure to introduce you to Professor Larry Washington, Lawrence C. Washington, but popularly he is known to all of us as Larry. And so Professor Washington is a professor at University of Maryland, and he doesn't need any introduction, but we have some very young kids here, the integrated MSc PhD students. So I can tell you that Professor Washington, of course, he is he's a light bearer, I would say, in the areas of cyclotomic fields, Iwasawa theory, cryptography, number theory, in elliptic curves, and all of you will be studying his books. His books are like on cyclotomic fields, on elliptic curves, on cryptography, on elementary number theory, on number theory. They are the books that people follow while learning these topics. And we are very, fortunate to have Professor Larry Washington with us. And, just to give you a little more information, that the number of theses, the PhD students, it's a staggering number, 40 students about that have done their thesis under Professor Washington. And he has, a long list of very, very quality publications research-wise. And otherwise, he's again, like Michelle, is into running, and of course he plays some instruments also. So this is about Professor Larry Washington, a little bit about him. And now I request Professor Larry to present his talk. The title of his talk is Class Groups of Real Cyclotomic Fields. So just to give you a little bit more information, I'm very happy that my student Mohit Mishra, this is a work that Professor Larry is going to speak, is a joint work with Rene Skoof and Professor and Mohit Mishra. So I'm really happy, doubly happy, I would say. So Professor Larry Washington.
Well, thank you very much for that kind introduction, and thank you very much for the invitation to the conference and for organizing the conference. I remember about 10 years ago, I was at a conference and I remarked that I felt very lonely because I was the only person who'd mentioned an ideal class group in my talk. So this series of conferences is definitely remedying the situation, because class groups have been dear to my heart for about 50 years now. Okay, so first of all, I want to say happy birthday to Michelle Waldschmidt. As was just mentioned, we're both runners, but Michelle has actually competed in the Mont Blanc Ultra trail run. So I guess we can say he's hit the highest levels in more than one area in his life. I also want to relate one story. I remember years ago, back in, I think it was 1988, there was a conference in Quebec. And it was a real question for the French mathematicians. Should they speak in English or should they speak in French? Well, Michel, being a true diplomat that he is, took the compromise. He wrote on the board in French and spoke in English. I was quite impressed. Nowadays, that would be no problem with PowerPoint and Beamer and things like that. But on a Blackboard talk, that was quite impressive. Anyway, happy birthday, Michel. So I want to talk about the real subfield of the nth cyclotomic field. So you take the full cyclotomic field, take the fixed field of complex conjugation, it's degree 2 below, and the question is, what can you say about the ideal class group? So the easiest part of a cyclotomic field is the minus part of the class group, the part that we're not talking about today. That's sort of a much easier part to talk about. But the real subfield is much more mysterious, partly because units play a role, and units are one of the hard parts of algebraic number theory. Okay, so one question is, how small can the class group be, or how big can it be? Well, I'll talk about both things. I'll start off with the small, and for the small part, it'll mostly be when n is prime, so the prime cyclotomic fields, and for how big it can be, it'll be when n is composite. Okay, so I want to start with just sort of a survey of a few questions that come up on real cyclotomic fields, and then I'll go on to the joint work that was mentioned in the introduction. So the famous conjecture, really the thing overriding conjecture now in cyclotomic fields is the Kumar-Van der Waals conjecture that if you have a prime P, then it doesn't divide the class number HP plus of the P's real cyclotomic field. So I'll always be using H as a class number, and H plus just indicates that it's for the real subfield. Okay, so it's been verified by calculations. It is true up to, well, 2 to the 31, which is like a little more than 2 times 10 to the 9th. That's quite a lot of computer calculation. So generally it looks like it's fairly true, but if you want to actually calculate the true value of the class number, it's very difficult. So these calculations up to 2 to the 31 were not calculating the class number. They were doing mod p calculations and showing it wasn't 0 mod p as opposed to actually calculating the class number. Now, some calculations have been done. It actually goes back to Kumar, and I always find this amazing. He was able to show that 4 divided the class number of the real 163rd roots of unity and the 937th. Now, really, what these come from this cubic subfields of these fields. That 4 divides the class number of the cubic subfields, and then this lifts up. It'll actually be something we'll see later, how class groups lift up or class numbers lift up. But I still find it very impressive that he was able to show that 4 divided the class number of the 937th roots of unity there. Okay, John Miller recently, in some very nice work, extending work of Odlyzko and others, showed I was actually able to calculate some of these by analytic number theory techniques. This is only like in the last 10 years, he was able to get the class numbers 1 all the way up to 151. And of course, you can't get 1 much farther than that because 163 gives you 4. But it seems like 1 is fairly common among the class numbers. And René Scoff devised a method that conjecturally calculates HP plus. It actually gives you a factor of HP plus that's conjecturally the whole class number. It's a really very beautiful method. And it turns out that most of the time HP plus is fairly small. But anyway, I want to just mention some possible heuristics for the Kumar-Van der Waals conjecture. The one that was floating around 40 years ago or so, a lot, was you say, well, look, HP plus, let's regard it as a random number. The probability that P divides a random number is 1 over P. So you want to count how many exceptions should there be to Van der Waals conjecture. It'd be summation 1 over P, which we know diverges, and that comes out infinity. Okay, so you expect infinitely many exceptions to Van der Waals. There's a little problem with this heuristic. It assumes HP plus is random mod P, and this seems very unlikely from the early evidence. Of course, we don't know what the class number looks like when P is really big. Maybe it starts growing after a while. Just like if you look at imaginary quadratic fields, you might think class numbers are 1, you have unique factorization fairly often at the beginning, but then suddenly the class number starts growing. We don't know if this is true or not for the real subatomic fields. We don't really know much about this. But you have a very slowly diverging sum. Summation 1 over P over all primes that will ever be written down in the history of the universe is less than 6, if you do the calculations. So really, the summary is we really don't know whether the conjecture is true or not, but we expect it's true for most primes. So if you want to have an idea what's true, you can assume the Kumar-Van der Waals conjecture, but it's hard to say. And there are other heuristics too. I mean, Mihalescu had some heuristics also, which indicate that probably the conjecture is true, but really everything's sort of conjectural at this point. So anyway, to move on a little bit, a question that was raised, I think it might have been raised by Serge Lang, is could the Kumar-Van der Waals conjecture actually be trivially true? For instance, is it possible that HP plus is less than P for all P? That would be the easy way to prove it. You could prove it analytically. Turns out the answer is no. Some work I did with Gary Cornell and Hugh Williams and Eric Say shows that for this prime, the class number is bigger than the product of these two numbers. Now, why do I write it the product of these two numbers? It's 2680. This real cyclotomic field has a quadratic subfield and a cubic subfield. And the class number of the quadratic subfield is the 2685. The class number of the cubic subfield is the other factor. And their product ends up bigger than P. So, and it's easy to show that the product of the two class numbers for the quadratic and cubic field lift up to the P cyclotomic field. In fact, it'll follow from something I say in a few minutes. But Serge Lang said that's not a good example. And he was actually fairly calm on this one, which is why I only put 2 exclamation points. Anybody who knew Serge Lang knew he got very excited by a lot of things. And he says, look, this is cheating. It's really not a good example because you could still say the Kumar-Van der Waals conjecture is trivially true because if all the factors you are less than P. So then Renee Scoff and I came up with an improved no, that namely the class number for this prime is actually bigger than the prime. So this actually used a family of fields invented by Emma Lamer back in about 1985 or so. And the factor on the right, 1566401, is actually a prime also. Actually, it's interesting, if you look up the review of this paper on MathSciNet, they give the prime 641491 as 641492, an interesting misprint for a prime. Anyway, so this says at least the Kumar-Van der Waals conjecture is not trivially true, that actually it won't be proved by analytic methods. It probably, if it's going to be proved, it has to be done by something much more algebraic. But also what I've done on this slide, there's a theme that the information we're getting of H for H plus is coming from subfields. For the result by Cornell and others, this is coming from a quadratic field and a cubic field. For this, it's coming from a quintic, degree 5 subfield. So that's going to be the way we get hold of class groups. So I want to mention a couple more things on small class groups. The conjecture of Weber from well over 100 years ago now, I guess, is if you take the real subfield of the 2 to the nth roots of unity, the class number always comes out 1. And he showed it was unconditionally that it was 1 for the first few examples. And John Miller, the same one who calculated those class numbers up to 151, showed that under the generalized Riemann hypothesis that Weber's conjecture is true up to n equals 7. And if you leave out the GRH, I think you get n equals 6 or maybe 5, I forget which. And an interesting result of Fukuda and Komatsu is that actually this class number is not divisible by any primes less than 10 to the 9. I mean, that's fairly good evidence that the class number is 1, though there are a lot of primes that are bigger than 10 to the 9. But anyway, at least this shows that you're not going to find trivial counterexamples to Weber's conjecture. And very similar result on real subfields of cyclotomic fields. Fukuda, Komatsu, and Morisawa showed that if you take the real subfield of the 3 to the nth roots of unity, it's again not divisible by any prime less than 10 to the 9. Okay, so this is what I want to say on small class numbers. But then the question comes up, how big can the class group of the, I wanted a plus in there. There should be a plus on this. How big can that be? And so for this, we're going to use composite n, because as before, we need a lot of subfields, and the more, if n's composite, you sort of have more control over the subfields. So here's the theorem I really want to talk about. It's joint work with Mishra, who's one of the organizers of this conference, and Skof, and myself. So if you have any finite abelian group, then it actually occurs as a subgroup of the class group of infinitely many real cyclotomic fields. So there was partial progress on this before, and then Mishra had a very nice preprint a couple of years ago, which actually took care of the case when G had odd order. And then Skof and I realized how to add in the even order. And Skof actually has a completely different proof that I won't talk about. It's a big cohomology calculation. So what I'll be talking about is much more in the spirit of what Mishra did in his preprint. Okay, so how do we go about doing this? Again, we're going to bring up groups from subfields. But first, I should just mention, you might wonder what happens for the full cyclotomic field. Gary Cornell actually showed that this analogous theorem holds for full cyclotomic fields. And this was using genus theory, that he was able to show that, given an arbitrary a finite abelian group, you could actually put it into a class group of some full cyclotomic field. But this is a much more algebraic proof in a sense. And it's using a technique called genus theory. Okay, anyway, here's the thing that gets us started. We want to be able to put together class groups from subfields. So I'm going to take 2 Galois extensions of Q, and I want them disjoint. Okay, so for instance, you could take 2 quadratic fields and get a biquadratic field. Okay, and with M and N are their degrees. And then the class group of the compositum field, so K, L put together, has a subgroup essentially the direct sum of the 2 groups from the 2 subfields, losing a little bit from the degrees. So for instance, if you take 2 quadratic fields, put them together and get a biquadratic field, then the class group of the biquadratic field, the odd part will contain a group that's actually the direct sum of the 2 odd parts of the 2 fields you put together. This actually, in terms of class numbers, can be proved by the analytic class number formula. But what it says in really what's happening is in this case of like quadratic fields, is that the class group, the odd part of the class group is essentially its direct sum. I guess there's a 3rd field in there, but then the even part is where you lose a little bit or gain a little bit depending on how things go. But this allows you to put things together. So let me just show you how it's proved. It's fairly easy proof. So we take a norm map from the class group of the compositum of the two fields into the direct sum of the two class groups, mapping to the norm of the two things. Okay, now if you take an ideal of, let's say, K, if you lift it up to KL and then take its norm back down, you get its nth power. Okay, the usual thing. But what happens on the other part? So I take I from K, lift it up to KL, take its norm down, what'll end up over there? Well, its norm to L is really just the lift of doing the norm from K to Q. That's because I took the two fields to be disjoint. And so Q is class number one. It's the lift of a principal ideal. It's still principal. So what that means is the image of this map contains the class group to the nth and 0 over here. Well, exactly the same way, you get it contains 0 in that. And the image, of course, is a group. So if it contains these two things, it contains the direct sum. And there it is. Well, what that says is, I guess the subquotient of this class group has essentially some of these two class groups in it. But just from elementary abelian group theory, if you get a subquotient, you actually get the full. You get that as a subgroup also, or as a quotient group. I mean, essentially, once you get it anywhere associated to it, it sits there as a subgroup. So the fact we get it as a subquotient is actually sufficient to get it as this as a subgroup also. Okay. So the other technique, and this is really a very key step, is if you take a number field, it's sitting between two cyclotomic fields. And you take a prime that doesn't divide the degree of F over Q zeta M over the lower cyclotomic field. Then the norm map from the class group of the top one to the class group of that intermediate field is surjective on the Q part of the class groups. Okay, you don't get surjectivity necessarily in the whole part of the class group, but on just on the Q parts. Well, on essentially everything is relatively prime to F over Q zeta M. Okay, let me show you first, before I show you how this proof goes, it's actually quite a good technique, but here's a standard method for showing class number divisibility. So let's say you have an extension L over K, and for some reason you want to show the class number of K divides the class number of L. Then you take H to be the Hilbert class field of K, so that's the maximal unramified abelian extension, and we'll have HL be the Hilbert class field of L. Well, if you take an unramified extension and lift it, it still is unramified. If it's abelian, it's still abelian. It just might not be maximal anymore. So it's going to be sitting here inside the class Hilbert class field of L. And now the useful fact, if you haven't seen it before, this is one of the main theorems of class field theory, is the Galois group of H over K is isomorphic to the class group of K. And the Galois group of HL over L correspondingly is isomorphic to the class group of L. Well, this is sitting inside. Now, a big if, that if's in boldface, is if L and H are disjoint, then you can take this and lift it up, and this has degree of the class number. So this has degree, the upper lifting has degree of the class number. And the full extension up to H sub L is the class number of the upper field. And just by divisibility of field degrees, the class number of K divides the class number of L. But you need this disjointness. And this works in some situations. For instance, it works if L and K are full cyclotomic fields. But we have something in between two cyclotomic fields. So here's what doesn't work. Namely, here's our K that's sitting between two cyclotomic fields. And here's its Hilbert class field, but we don't know its disjoint from Q zeta N. How could we get it that way? Well, if we had the degree of Q zeta N over K prime to Q, then it would have to be disjoint. Because we could look at the Q part. Okay, we don't have to look at the whole thing. But if you had this degree of q zeta n over k prime to q, you'd have enough disjointness to lift the q part of the class number and get the result. But the problem is that's not what we're assuming. We're assuming k over q zeta m is the part that's prime to q. So it's the wrong part for getting this argument to work. But the thing is, from our construction that we'll come up with in a few minutes, it's k over zeta m that we have control of. It's q zeta m over k, q zeta n over k that we don't have control of. So we can't use this argument. So we have to do something a little different. And so here's what works. And here's where we, here's how it goes. So we have our, what we're going to do is we have this k, and eventually we're going to go up to q zeta n up here, but we're going to go from q zeta m to q zeta n by adding on primes one at a time. So I'm just going to show you the first step, and the others are essentially just by induction, the same idea. Okay, so you take k over q zeta m, and you want to lift it. Well, no, you don't want to lift it. You want to lift the class field. So here's the q part of the class field. HQ is the q part of the class field. So it's a maximal unramified abelian extension that has degree of power of the prime q. Okay, we want to lift it up to the class field of q zeta mp. So just adding k contains zeta m. We want to add on one more prime, make it zeta mp. So we want to lift the class field. Okay, and that will give the divisibility of the class numbers. Well, actually, it does more than divisibility of class numbers. It gives divisibility of class numbers, but if this lifts disjointly, it says the norm from this class group to this to the lower class group is surjective. And that's what we really want, is the surjectivity of the norms, not just divisibility of the class group. But if you go through the formalism of the Artin symbol, you actually find that the if the class field lifts disjointly, then the norm is surjective. Anyway, well, here the HQ over K is unramified and it's a Q power, because I'm only looking at the Q power part of the class group. There's no Q power in K over Q zeta M. That's by assumption. So let's take if HQ and K zeta MP are not disjoint over K, then there's some intersection here. It has to be, it's still going to be unramified and it's going to be a Q power. Well, where's this Q power unramified part going to come from? Well, going Q zeta M up to K, there's no Q power. We got a Q power up here. Now let's go the other direction. From Q zeta MP up to K zeta MP, there's no Q power. So the unramified Q part would have to come from Q zeta M to Q zeta MP, but that's totally ramified. There's no Q part that could be unramified here. And so what that tells us is actually that HQ and Q zeta MP are disjoint over K. So the Q part lifts, and therefore we get the class number divisibility, because this part sits in the bigger class group up of Q zeta MP. And so this gives you divisibility as you start adding in the primes one at a time. And that's enough to get the divisibility of the class numbers. So let's see, what did we just prove? Let me go back to the thing that the norm. So what we really, I just sort of indicated that the class number of F divides the class number of Q zeta N. But what really happens is that we actually get a surjectivity of the norm on the class groups, on the Q parts of the class groups. Okay. So that was the technical part. So now, how do we actually prove the theorem? Well, we write the group as a two-part and an odd part. And you can guess what Mishra did was his work was taking care of the two prime part, and then we saw how to add on the two part similarly. Okay, so we need one way to do it is a result of Yamamoto and Weinberger, proved in Yamamoto did it in 1970 and Weinberger did it again in 1973, that if you have an R, there are infinitely many real quadratic fields with class group containing an element of order R. Okay, so what do? That says you can put together, if you have an odd order abelian group, so it's a direct sum of cyclic groups of odd order, you can take, for each of these odd orders, take a real quadratic field that has that odd order in its class group. Now take a compositum of them. And by the result I had earlier with the for the compositum of two groups, when we put together real quadratic fields, we only have problems with the two part. The odd parts, we get the direct sum. So you get the class group of F prime contains a subgroup isomorphic to the odd group we're looking at. And now this group is sitting between Q, which is a cyclotomic field, a rather trivial cyclotomic field, and by Conjecture of Weber theorem, it's sitting inside the let's say n first, whatever, cyclotomic field. So now we're looking at the odd part. Well, remember, we didn't want to go Q zeta n1 over F prime. That could be some degree we have no idea what's happening to, but F prime over Q is a degree 2 power. So that means, from what I just proved, that the class group, the norm from the class group of Q zeta n1 down to the class group of F prime is surjective on the odd part, because the only part you lose is the degree of F prime over Q, and that's a 2 power. So that tells us that F prime over Q is, well, it's power of 2. So that tells us that you get a surjective map from Q zeta n1 to F prime, and that's F prime has a G2 prime in its class group. So that says Q zeta n1 has a subquotient isomorphic to G2 prime, which actually says also, therefore, by abelian group theory, it has a subgroup isomorphic to G2 prime. Okay, but now we need to use cubic fields. Now, a result of Uchida says if you're given R, there are infinitely many cyclic cubic fields whose class group contains an element of order R. So we put those together. And now, since we're putting together cubic fields, the only thing we can lose is 3 part. Everything works very nicely on the other part. In particular, we can get the 2 part of the group we're looking at. And now, our field, by Conjecture of Weber, it sits between Q and some other cyclotomic field, N2 cyclotomic field. So we get because F over Q is only 3 power, that says the 2 part of the class group, the norm from Q zeta N2 to the class group of F is a surjection. Okay. So we get a surjection. Now we got to put things together. So you take the least common multiple of N1 and N2, and that says the nth cyclotomic field contains N1 and it contains N2. Now, actually, from the result I had before, the class group of Q zeta n surjects onto the class group of Q zeta n1, and it surjects onto the class group of Q zeta n2. That's because just for any cyclotomic fields, if one's contained in another, the norm map surjects, and that follows from actually stuff I said before, or just lifting the class group in that case. So this class group of the full cyclotomic field, I haven't done the real subfield yet. It surjects onto the odd part of the class group of F prime. So what it does, it surjects onto Q zeta n1, and then the norm keeps going down to class group of F prime, and so it surjects onto the odd part there. And going through Q zeta n2, it surjects onto the 2 part of the class group of F. So individually, it surjects onto both. And now, these norm maps actually factor through Q zeta n plus. Why? Because F prime is totally real and F is totally real. So they're both actually contained in the real subfield of Q zeta n. So the norm factors through. And now that says, since the class group, the norm maps the class group onto G2, onto the class group of F prime, it has a subquotient G2 prime, and it also has a subquotient G2. And since G2 prime is the odd part and G2 is the even part, the direct sum is in there, and G was isomorphic to G2 prime plus G2, and therefore the class group has a subquotient isomorphic to the direct sum, G2 prime plus G2, and therefore it has a subquotient isomorphic to G. Well, once you have an abelian group that has a subquotient isomorphic to G, again, by just playing around with the structure of abelian groups, it actually has a subgroup isomorphic to G, and that proves the theorem. So I guess that's it. So I guess I finished a little early. So thank you again for the invitation.
Thank you so much, Professor Washington. It was a wonderful exposition of a beautiful